Good afternoon. In this lecture, we are going to talk about the different vulnerability analysis and mitigation of cryptographic libraries. So, specifically in the previous lecture, we talked about how to design and integrate different cryptographic modules and how does it fits into the big picture. Now, we are going to talk about if you are a designer who is designing it, how do you analyze whether it has any security vulnerabilities and flaws, and we are going to talk about different ways of looking at it, and all of these ideas you already know. It's just that today's lecture I am going to focus or apply those ideas on the cryptographic libraries only. So, to be specifically what I am going to focusing on, this is a summary, whether you are developing hardware cryptographic IPs or which people call as accelerator once you implement, or software cryptographic IPs, the different key sizes, they have a set of known vulnerability. So, for example, in AES in software version, the reuse of nonce is a well known vulnerability, and similarly counter overflow, empty, initialization vector, timing, fault injection. In contrast, in the hardware side, you will have some of the similar things as well as you will have ideas like power side channel, timing side channel, clock and reset vulnerability on all that stuff, and some of those are not applicable for software domain. Some of them are common, some of them are not common. And in the security community, this true random number generator, PUF, odometer, they are typically not referred as cryptographic module, they are referred as security primitives, but whatever it is, they also have their own vulnerabilities. For example, random number generator is basically based on entropy. If for any reason somebody can reduce the entropy based on certain types of attack, then that is going to be a problem. Fault injection would be another type of attack, signature bias, verification, low resolution fault injection, and so on and so forth. So, objective of a designer is then basically can we do iterative refinement. So, you design something, then you know the vulnerability, you implement that mitigation, then you check your vulnerability and tool analysis again to make sure that the security strength has improved, whatever your metric is. So, what I am going to talk about, what are the analysis tools people use or should use, and then what are the metrics. So, I am going to talk about lot of vulnerabilities, but our context is still the same. You have your system, firmware, hardware, primary focus would be security engine or cryptographic IP in this discussion, but as you know these techniques are useful for any of the other modules as well. So, let us start with Google WichiProof project. So, how many of you know what is WichiProof? Although it has a proof, it has nothing to do with the verification. WichiProof is this one, it is a smallest mountain in the world, it is 42-meter height, this particular one picture did not come correctly. So, that is WichiProof, and again this picture has nothing to do with Google WichiProof project. Google's view was instead of trying to solve everything and fail flat in the on the face, let us try to solve something that is tractable, achievable, and we can solve it. So, all the interesting stuff ends right there, and so if you go to this GitHub page, they maintained a set of tests, and I kind of last I counted it is around hundreds of tests, and what that test gives you, if you have a set of software libraries, you might be downloading from libgcrypt, let me say it again, libgcrypt library, GitHub page, if you download those or you design on your own or whatever you do, as long as it is a software library, those tests will work, and you want to run those tests on your cryptographic library to make sure at least it does not have the well known problems. That is basically the idea of these tests. These are not formal verification, these are simulation tests, but nonetheless it is all at least check some of the bare minimum requirements. So, for example, for of course, some of them are applicable. So, for example, for elliptic curve cryptography it is invalid curve. You are giving the point or giving a curve, that is not a valid curve, and the nonces, if the nonces has kind of low entropy, those are biased nonces, and there are well known list of attacks. I can't even pronounce it, I won't even try. So, there are many more, about hundreds of tests, each is unique, and that basically covers all the well known attacks on cryptographic library, at least software versions. Any question on Wikiproof project? So, if you are planning to download or write, this is the starting point, then you can test on your own. Now, this one is easy. So, I wanted to start malicious implants. Anybody remember the synonym of malicious implant? In software, what is it, and hardware, what is it? That would be the question on Friday. Malware for software. Who can say what is the synonym in hardware? Hardware Trojan, right. So, for the malicious implant, for the hardware, we kind of looked at it. There are different types of Trojan. This is combinational, this is sequential, this is information leakage, this is and so on and so forth. That is a system level Trojan. So, then for cryptographic library, what you want to do? You want to scan for those, and when you scan for those and you believe you have a mitigation for it, which I will talk in a moment, that scanning tool you want to use it again, just to make sure your metric improved. And what kind of metrics people normally use? We talked about it, number of activated rare nodes, assumption threat model is rareness is the number of rare nodes, number of rare branches, number of rare triggers, and so on and so forth. And then you basically want to kind of on a security level, you want to figure out where your that module is, cryptographic module is, and then you do the mitigation to kind of take care of it, right. Now, anybody knows, if I know this number is not good, how do we reduce number of rare node? What can we do? If there are rare nodes, there are rare nodes, that is the property of the design. What can we do? Didn't we talked about rareness reduction as a technique? One of the objective of rareness reduction, there were two techniques we talked about, at least two. One is area optimization. If you can synthesize it for the least area, that is guaranteed to have the less rareness, which basically means it would create non-rare nodes among all possible synthesis methods. We also talked about design diversity, maybe another implementation, instead of carry look ahead adder, you might want to consider ripple carry adder if it has less rareness. So, similarly, there are different other ways of solving this problem, but no matter what mitigation you do, you still want to run the same tool, same technique to make sure you are somehow improving and going towards this line. That is basically the objective. Now, the way in cryptographic module people use, of course, your threat, based on your threat model, you figure out what your suspect candidate, and remember it does not have to be rare, because each of the steps are independent. You can manually add some more signals if the designer said, I believe this is where I suspect something might happen, this came from some part of the world, or if you believe that if an attacker knows you are only focusing on rareness, they want to focus on rare as well as a little bit of non-rare. Of course, the space is huge, millions, but if you want to put some of the non-rare nodes, that is fine too, that is your starting set. For different techniques that I talked about, different ways of whether it is statistical, whether it is SAT solving, whether it is ATPG, different ways. Once you have suspicious signals as input, different ways you can generate the test. Now, you have basically golden model and your implementation, whatever implementation you compare and you check for output. Now, first question, for comparing output, we need a golden model. Where is the golden model in cryptographic story? Did we talk anything that gave you a feeling we have two models anywhere? If you are developing a elliptic curve model, all you have that VHDL Verilog description, where is your second model? Did we talk anything? No? Didn't I say 20 times leave G crypt? So, you can use your software model here and you can use your hardware model here, that is how the community uses it actually. because this one is very stable, all over the world people used it. Hardware models are not available, every company develops those, they sell it, they make money out of it. So, you are going to implement on your own, and if you are going to implement that, the problem is likely to be here compared to there. So, it is relatively golden. So, that is and because input output all that is fine, primary thing is message and encrypted version. No matter what nonce you use and whatever you do, the encrypted version is going to be exactly same if key is going to be same, right. So, any questions on this idea? We have the golden model, we have implementation whatever you have, and then if you have another golden model, that is fine too. So, for example, you developed a VHDL Verilog code, you tested for 6 months and then you sent it for synthesis to third party, or you sent it for fabrication and fabricated chip came in. So, something you have a actual silicon running and you have VHDL Verilog model running, you can do that too. It is just that do not try running same time, this is going to run at gigahertz and simulation is going to be at megahertz. It is just that you compare the final result. So, this technology is going to work only in one scenario of Trojan scenario. We talked about so many possible scenario. Anybody remembers in what scenario it will work or what type of Trojans it would work? If you recall, Trojan has different types of trigger and payload. The payload of functional change is the only one where it is applicable. A Trojan that changes the functionality. If it does not change the functionality, you have nothing to compare. If it changes a power footprint, then probably you have to do the power difference, which would be a side chain analysis. Now, I am going to talk about finite state machine vulnerability. If you looked at it, the cryptographic module itself has finite state machine, each of them, because they have different states. Yes, please.
If it is not functional change, how do you basically detect the other kind of Trojan? So, question is for functional change Trojan it is easy to detect, right? It is not easy, but at least you have a chance to detect. But what about the other kind of Trojan that does not change the functionality?
So, let us take any other example. So, in the Trojan case we have different types of payload, right. So, let us write it out. We had payload of a functional change or functionality, that is what we talked about, and then we have the parametric changes. We have parametric changes, you have many other. So, some of the parametric one, for example, it changes the power or thermal profile. So, if it is a power profile, then your comparison should be power, but then you need to have a golden model. Problem is most of the time golden model does not exist, because you need a golden hardware model. If somebody fabricated already a golden hardware, why on earth they will go and fabricate another non-golden one? Right. The way people normally look at that, even try to solve that problem, that people do not fabricate all the millions of chips at the same time. The first batch they probably fabricate 5, 10, 20 or 100, and then they kind of do testing and all that stuff, and those are assumed to be golden. They are very carefully crafted, very customized purchase. Instead of when they are asking for millions and billions, things may go wrong. But otherwise this is kind of, that becomes tricky, that becomes an academic exercise. That is why half of the world do not believe in this in the first place. So, now for the finite state machine vulnerability, it is important, because if you look at any cryptographic algorithm, it goes in multiple rounds or phases. Even in AES with 128 of 10 rounds, those 10 rounds is actually 10 state in a finite state machine. There is no other way you can implement it. You have to have, whether you are writing case statements or whatever equivalent in your VHDL or Verilog, case basically round 1, case round 2 and so on and so forth, all the way of round 10. You do not jump to round 10 unless you have done R1 through R9. So, therefore, there has to be some signal, some if statement, whatever way you implemented, it is going to be a finite state machine. So, here is a simplified version, instead of 10 round, it is basically wait and wait for data, initial round, and then in between. So, let us say it is a 10 round, this is basically the first one, this is basically 2 to 9, and this is basically the 10th one, but that has to be counted. So, it is possible you can implement this using one state, but then you have to put a counter where you are counting how many times I entered. But whatever it is, no matter which algorithm you look at, the core part of it is finite state machine, and therefore, attacks on finite state machine needs to be considered. Now, data path could have problems. So, for example, the laser fault injection or just normal fault injection, even the data path, if you have a value of 0 1 1, if any of them flips, that is also a problem. We need to look at that vulnerability, but finite state machine, the specific one we are going to look at, that depends on what threat model you use. Here we are using these 3 threats or 3 kind of things we call as vulnerable, and this work actually got integrated in Synopsys Spyglass, which is worldwide everybody uses to just check their designs. So, do not care states, do not care transitions, and the laser fault injection vulnerability. So, what is the key idea? Basic idea is, if you have drawn a finite state machine like this one, do you have states hanging here and there that nobody knows? Those are the unspecified ones, nobody knows about it and nobody tested it. An attacker is likely going to sit there and then do laser fault, whatever it is. So, the first question I am going to ask you, why on earth these 3 states are there? I did not write it my VHDL Verilog code, you did not write it, then where did it came from? I am looking for few hands, those of you write VHDL Verilog code or synthesize. Where did this state came from? Just do the little counting with me please, 1, 2, 3, 4, 5. How many extra are there? 3, 5 plus 3, does that give you a clue? 2 to the power 3 is 8. So, in your mind, my mind, when I wrote the code, I had 5 case. I did not put the default, or I do not care, right, even if I did not care. But because there are 5 states, whether the synthesis tool do binary encoding, one hot encoding, it really does not matter. It needs to use 3 bits. A state register it need to use, that register needs to have 3 bits, and I can assign some values. I can assign 0 0 0 here, 0 0 1 here. Of course, that encoding is important, it is not random, but I am just making it random, 0 1 0 0 1 1, and then this one is let us say 1 0 0. But the other 3 also would be named in some way, 1 0 1 1 1 0 1 1 1. So, the amount of do not care states you have, that is the vulnerability you kept it for attacker to attack different ways. So, it is not a good idea there, it is not even a good coding style in any good company's coding book. You have to have a default statement, you have to have encoding for those. So, that is about that is actually easier to solve. So, how do you mitigate this problem? Just add a default state, add more states, they may not have anything, just maybe print something saying why are you here, right, trespassers will be prosecuted or something you print, then you know that state should, nobody should have gone to that state in the first place. Register should not have assigned that value under any circumstances. But the bigger problem is the next one, do not care transitions. If you have 8 state, how many possible transitions are there? N square, right, n square possibility. So, 64 possible transitions, no matter how you count. Let us count together 1 2 3 4 5 6 7 8 9 10, total 10 transitions you are going to verify. Remaining 54 transitions nobody is going to verify, nobody is going to check, and those transitions are going to happen due to laser fault injection. Can anybody help me, how would it happen in laser fault injection? I did not do the state encoding right, just to illustrate. I should have, whom did I give 0 0 0? I did not give anybody? Wait key. What did I, it looks like, oh, I wanted to write 0 0, okay. that is 0 0 0. Now, if I flip just the leftmost bit, I already reached the final round. Through laser fault injection I talked earlier, I reached the final round. So, and if my laser fault injection capability is 1 bit, that is good enough for me to do that. And so, but remember that transition does not exist, but we never check that transition. If that transition happens, what to do? We do not have any assertion. So, therefore, that attack is possible. That is why that is a vulnerability. So, this do not care states, mitigating that vulnerability is easy. Adding another 54 transitions, I do not think anybody will like that idea. No designer in right mind will accept that area overhead and all that stuff, but nonetheless that is similar stuff for this. I will zoom in later more, but laser fault injection vulnerability, computing those vulnerabilities. So, how do we compute these vulnerabilities in the first place? So, do not care states is as simple as number of unspecified states over all number of states. How do I compute? If you have b bits of encoding, 2 to the power b is your total number of states. Out of that, how many states you have, and then total. In the previous example, we have 8 possible states, 5 was basically specified over 8, 3 over 8 is what the probability, this probability is. So, for do not care transitions, this is little complicated for a reason, it is not important, but what is important is this do not care state. If you look at it from a layman terms, if you have b bits, total number of states are 2 to the power b, total number of transitions are n square. So, that minus how many transitions you already have divided by 2 to the power b square. That extra complexity is there are transitions, there are state machines in cryptographic library where you cannot have 2 to the power 2 b transitions, because number of inputs that drives that finite state machine is not going to have those many states and those many transitions. So, that is why if n is the possible inputs to the finite state machine, if it is less than b, then it is a slightly smaller bound than that, but either way it is still a very large number. This vulnerability is huge, and there is not much you can do, at least by adding more transitions. The laser fault injection vulnerability I will zoom in more, but the question is how many states are vulnerable, and then over the total number of states. This I will talk about.
So, one
Yes,
question here. So, you mentioned that the Synopsys spyglass has those checkers, right? So, what it exactly checks there?
So, Synopsys spyglass actually is kind of checks a lot of stuff. It is like a software analogy of linting tool. It checks memory buffer overflow and all that stuff. So, they did not have any security checking. So, this is one of the first one they introduced, but that is a $1 billion product, or they are one of the second or third biggest component after design compiler. That is what they sell. At the RTL level, people just run the spyglass and gives all kind of the clock tree violation and all that stuff very early, so that people go and do the layout, and then they figure out, oh, I have this parasitic effect. And so, as much as possible they pushed it up in the RTL level, and so that they can check all those scenarios, different kind of path and delay.
So, it is basically check how many states are unspecified in your FSMs.
It is more like a warning message, and designer may look at and say, hey, I do not care. It is more like it analyzes, and designer will say, okay, I understand, I do not care, that kind of stuff. So, but this one, the solution is also implemented. I will zoom into the LFI.
So, threat model is like in the downstream somewhere somebody use those do not care state to implant some.
They will use those unspecified states. They will make a sitting on there, and then they, or maybe install a Trojan there, which will stay there as it is, and with laser fault injection or otherwise they will make the transition to another state. So, basically hiding in the unspecified functionality. So, LFI will talk later. So, I did not spend more time. So, information leakage in the security community, two areas is going to stay for a long time. One is side chain analysis. Many people think they are same, they could be different. information leakage and side chain analysis, or those areas are going to stay active. The chances of the hardware trojan and puff and the logic locking is likely to go away, because funding has kind of dried out those areas. So, that is the indication. So, information leakage, as the name suggests, if you have a design, where you have a secret S, which of course, secret S will travel. It is a design, it is connected somehow, but there may be a if statement here, if privilege then do something, right. But if somebody can mount an attack on that variable P, then and make this true even when it is in user mode, then that data can transfer. That is why in the information leakage analysis community, there are two ways of looking at it. One is statistical analysis. Can I compute the probabilities? If you recall earlier, we talked about if you have an AND gate and the probability of both input is 0.1, then output has a 0.25 probability of being 1. So, if you can propagate that way, you compute a probability of, first you have to identify what are your shared values. In case of cryptographic library, it is basically the key, wherever is the key variable or any other variable which can directly imply the key variable, you create a set of that, and then from that set you kind of propagate this static way of probability calculation all the way to the output, and it is quite likely all variables will propagate to the all outputs, but the probability values would be very low. Then that tool would give that whole listing of the leaky paths, and odds are all the millions of paths would be listed, nobody would be interested, probably the top 10 path would be listed. Designer looks at it and say, yeah, that is fine, that has a privilege, that would be fine. In fact, this idea of leaky path computation or information leakage, it is not just for hardware cryptographic library, even for software cryptographic library. One of the well known concept or compiling cryptographic library, Dr. Karfa is world leader in that area, has been the secure compilation. In the basic idea of secure compilation is the following, and we are talking about secure compilation for cryptographic libraries only. So, secure compilation idea is following. If you have, let us say, a C program, think of your cryptographic program, cryptographic library program, let us say AES, and when you compile it and get the binary, this compiler job is to ensure the performance is good, the area requirement is less, power dissipation is less, but suddenly we are imposing for cryptographic library that it should not create binary which is vulnerable. How do you define vulnerable? Let me use the information leakage example. On the C, I compute the information leakage function and find the leaky paths, or let us say just take one path, topmost path, what is the probability of that path, let us say 0.25, or find n number of paths. The definition of security in this domain has been, after compilation, the number of leaky paths should not be more than of number of leaky paths in the original code. Ideally, you do not want to have any leaky path here for a cryptographic library, ideally that should be the objective. But the point I am trying to say is, even for software cryptographic library, when you compile, when you compute the leaky path, remember if privilege statement will be there, key will travel through the design, that is, otherwise if key does not travel, how the computation happen, all these XOR and encryption, how does it happen, but you want it to be happening in a specific mode. And in fact, many interesting situations, security engine maintains the key. When security engine through that bus request the AES to do the computation, it has to transfer the key through this path. So, it is not the key is staying stored inside the AES, that would have been ideal. If you can protect the AES, you are done. So, key will travel through the bus, and that causes this leaky problem. But as I said, in software domain things could be different, but ideally you want to create a situation binary has no leak, no leaky path. But as you realize, when you have a code, when you have anything, it would leak. So again, if you are interested in doing, you may want to do PhD with Dr. Korfa on this area. Any question? Yes, please.
One query, sir. Previously, when it explained us about the homomorphic encryption, sir. So, like you have suggested that the security enclave that key transfers to the AES, can homomorphic encryption be used there?
So, if you do homomorphic encryption, you do not need AES, right? You do not need AES, but remember homomorphic encryption solves the problem of computing with encrypted data, right. But when you are doing the encryption, homomorphic encryption does not do that. So, you are using AES, key is traveling. So, all these problems still remains. You are going to use your AES software library, AES hardware library, those will remain. In the computing frame, you do not need trusted execution environment, that is all it is. Any other questions? So, the information leakage, all I wanted to highlight, information leakage problem is an interesting problem in software domain, hardware domain. How people exploit this leaky path, that is different. Software domain it would be different, hardware domain it would be different. For example, if the information does not leak, then some of these side channel attacks will not be possible. In the microarchitectural attack that I talked earlier, cache timing attack, the value gets transferred to the cache, right. It should not have propagated that time. In here, based on a side channel, you are kind of, so it's a leak, but it's not the leak I just talked few minutes ago, the leaky path. It's not actually coming to primary output. We don't care about primary output. We are trying to find how much power you consume, and by looking at the power footprint, we are trying to figure out which computations you are doing. That is the information leakage, but not the one I discussed. So, you are still finding some information about the computation, right. And of course, this is a simple power analysis. These days people use more sophisticated ones, because attacker knows you are going to do this. So, they will try to hide. So, then there are sophisticated one, differential power analysis, higher order differential power analysis, and so on. Now, if you want to do at the program level, at the software level, this would also work at the RTL level analysis. There are at different level you have different types of analysis, and there are information flow tracking techniques. So, static one I talked about, you compute the probability in your design starting from the secure path all the way to the output, you compute the probabilities of each of the gate. If it is a gate level, that is a static one. In the dynamic one, you can instrument with the tagging. So, for example, if B in that domain, this is called tainted, although technically it is not be tainted, somebody is secure, it should be respected, right. But in the community they have somehow called them tainted. If B is tainted, and if there is an assignment like this, C would be tainted too. So, that is why this tagging information happens. This is known as explicit information flow. Implicit information flow would be here C is equal to B, which is fine, but there is also another component, and this component part, because it is a part, this assignment is part of a if statement. So, that means information about A is also percolated here. So, that is why if A is true or B is true, C is going to be true. So, this is kind of implicit information flow. Any questions on difference of explicit versus implicit? Explicit is if B was 1, C will be 1, and if anybody is printing C or have the ability to view C, they know about B, that is obvious, that is the explicit. Here it is implied because it is not direct here, but because it is inside the if statement, this would not have been executed if A was not true. So, if this got executed, then you know for sure A is true. If A is your secret variable, then and if you print a print on C, and it, let us say C was initialized to 0 by the attacker, if C comes to be 1, then you know C was modified. If that is the only place it modified, not here, it was made 0 here, then you know for a fact A was true. May or may not be, because B could be true also. Either way, it would not enter if A was not true. So, then you know the secret information of A is percolated to variable C. Now, technically this is correct, but this is conservative. Let me illustrate. If you have an AND gate, so information flow says any function, if input has taint, output will have taint. And if I apply that argument, if I have A and B and output is C, it should give me a function that C is always the taint propagation, if I use C underscore taint, A underscore taint or B underscore taint. I am not saying it is wrong, but it is not conservative. More precise answer would be. So, these are all these are imprecise, implicit imprecise, explicit imprecise. Why it is not 1? Because we know for AND gate who is the dominating input, 1. If any of them is 1 and we are interested in B, B is my secure variable, it actually propagates. But B if A happens to be 0, B actually does not propagate to C. So, this should be a precise information flow tracking. If you do the probability, do the computation correctly, then you have to do a model, different truth table. There are all these problems have been solved by Mohit Tiwari from UT Austin. So, basically then who will flow that precisely defined at gate level, there are researchers who defined it at RTL level. There is a lot of work in this area. Any question on precise versus imprecise and implicit versus explicit? Precise basically means we do not go by the conservative definition that output is always tainted if any of the inputs are tainted. Now, we are making an exception if the controlling variable is not my security gadget, then that variable does not contribute, that does not propagate. Oh, controlling variable is not security gadget and it is set to controlling value, which is 0. OR gate if it is set to 1, then does not matter what is the other variable, output does not get reflected on that. Any questions? So, if you simulate it, if you simulate any of these design, tag it, and all you observe, the let us say in this particular example C is a primary output variable. If you get certain value or change in the primary variable, then you know value got propagated during simulation. It is not a guarantee. So, that is why what formal verification people do, they basically figure out always A, which one is variable, let us say B underscore T not equal to C underscore T. So, they basically check this property that does not matter how many possible paths are there, these two tags should never be same, they should not track each other. You can write different way, B underscore T implies not A underscore T or vice versa. Then that would give you a formal guarantee. You still need to do the tagging, either you do simulation does not guarantee, simulation only says the time you simulated information did not flow. But if you can check it, then you can guarantee that that travel indeed did not happen, will never happen. Now, I am going to talk about information flow in different other, I chose one or two cryptographic algorithm, elliptic curve, the encryption one, this is the encryption standard. And this has different modules, start, multiply and in that order. So, if you are trying to see through side channel, you are going to, so remember in side channel couple of important points. One is finding the boundary, which component is where. Second thing is getting rid of noise through different kind of differential analysis. And so, therefore, doing the timing right, putting the right boundary, that is one of the key kind of area or work. And once you do that, and also another thing is unless we apply correct input, information may not flow. Because remember in information flow tracking, or a shared variable for it to go there, you have to set certain variable right to increase your probability. Remember the AND gate? If you had an AND gate and the secret value you want to pass, the controlling value is set to 0 for some reason, then it is not going to work. You have to make sure that value to the controllability, if you remember, you need to find input that would set that controlling value to 1. So, that if there is anything in the secured transfer path, that can flow through. So, therefore, important test generation is also important. You cannot just simply do side chain analysis, you plug in something, get something, it is not going to work. So, you have to get traces where a specific computation being done will produce a significant difference in the something getting computed, something not getting computed shows you a difference. If everything looks same, you will not be able to distinguish them. If somebody is multiplying with the 10 versus multiplying with 20, you want to differentiate it. So, once you have that, and then typical different stages of computation, it could be static power, simple power analysis or differential power analysis, then you kind of check, can I distinguish it? If I can distinguish it, if I can find it, if I can figure out the key, then basically I am successful. And of course, there are these errors of false positive and false negative, and you want to kind of handle all of those, and there are mechanism to kind of, if you partition it right, then that problem can be addressed. And when you partition, so I just wanted to show you something, when you partition in different ways, too fine or too high, this type 1 error and type 2 error is kind of has a interesting characteristics. If you have too many partition, then your type 2 error is going to go down. Let me just double check, type 2 is false negative and type 1 is false positive. And if your partition is kind of less, then your type 1 error is kind of down. So, therefore, you want to find a area, this marked with yellow here, you want to find a area where you want to perform your experiments where both of these errors are in kind of controllable range. And here are some stuff, but the thing I want to talk about, although I did not introduce these ideas earlier, I will briefly talk about shuffling. You already know, AES already has a shuffling operation there. Blinding, as the name suggests, blinding is a mechanism of, think of you are encrypting, you want to give some data to somebody, but you do not want that person to understand it. So, typical one of the way to do is kind of blinding would be just you kind of encrypt and give the data, but it is similar to homomorphic encryption, you have to rely that such a computation actually exists where they will return the data to you. But even if you do any of these stuff, the blinding, of course, without mitigation the attack is very successful. Even with some types of mitigation, for example, blinding and what is this 2, one of these scenario or one of the run, it was broken. So, blinding, simple blinding did not work, shuffling and blinding or just shuffling, global shuffling, that all worked for Montgomery multiplication, which is part of the ECC code. One of the function of that multiplication is part of it. So, you want to really analyze module by module and all that to figure out which one is, and the way you kind of do different double addition and all that Montgomery, what you want to basically figure out. So, minimum alpha value, which is basically this color, this green color, any stuff that going below this color, that basically means you can statistically guarantee that you can figure out those values, and in this particular case just happens to be these red ones. So, Montgomery multiplication is just fine, and so normal multiplication, these blue lines will just go below here. If you use just normal multiplication, that is actually a mitigation on elliptical cryptography. We kind of extended this idea to a domain that I want to introduce to you. It is called cryptographic instruction set extension. Now, the motivation for this one is the following. So, software cryptographic algorithms, you have all these reconfigurability that makes it pleasant, but in hardware cryptographic algorithm everything is like kind of rigid and tight, but hardware is fast, right? If fast, it somehow feels like more reliable. software is kind of flexible, but it is not really fast, not most power efficient, and somehow gives a feeling it is probably not the most secure one. So, that is why the RISC-V community came up with this idea of cryptographic instruction set extension, where you basically have a set of instruction set and some modules to kind of combine the advantages of software cryptographic library and hardware cryptographic module. Let me just do this animation to see if it works. So, think of a cryptographic algorithm, it does not matter what algorithm it is. This I could be AES, this could be elliptic curve cryptography, one could be RSA, it is just two cryptographic algorithm, has some sub computations. Remember, many of them invoke SHA, you can think of SHA as one of the invocation. And if you look at the common color, if I did it right, so this color is common, this function is called at different stages. Why am I getting same color, maybe different color? This color is same, this color is same. So, basically these components are same. So, what RISC-V community did, they analyzed all these cryptographic libraries and figured out what sub function is same, and they designed an instruction set for that. Let me see if I have the. So, that basically means, remember, add, subtract, multiply, divide, all these are kind of granular computation. Somebody somewhere in the world figured out that no matter what program you run, bubble sort, insertion sort, searching, whatever you do, this add, subtract, multiply would be needed. That is why they created those modules, that is why instructions are created. Same analogy RISC-V community did, that if you look at AES, let us not implement whole monolithic AES, look at sub functions of it and implement them, such that those sub functions can be used. If somebody wanted to implement ECIES, they can implement it. So, that means let us think of AES, and let us say AES would involve, by using this analogy, CR1, it does not matter what it is, CR1 and CR3. Maybe ECC will use CR1 and CR2, maybe few more. So, the key idea is those are the instruction, corresponding modules are over. So, corresponding modules are these, similar analogy to add, subtract, those are common functionality between different programs. Think of cryptographic modules also as program, these are the common elements on those programs, and corresponding instructions has been made. So, we looked at this problem and we thought, well, nobody did any security verification on them, why not us? So, then we basically looked at and analyzed them. There are a lot of interesting problems and challenges. So, there are many interesting problems and challenges, but basically flow is pretty much the same as any other flow. Here only additional thing is, for each component we are kind of evaluating them once, are they vulnerable, then each component we are evaluating on the whole system. And why, I will give you an analogy why we are doing this without using cryptography name, I will give you the analogy. So, for example, when you design a processor, right, you have a processor and then you have a memory. Let us start with the memory. Let us say you designed a memory, you tried testing it all possible ways, but you observed for some of the negative numbers, negative 5, negative 15, negative 35, it is failing. Still you wanted to take a risk, put it into the system is working just fine. Nobody found that problem ever. Can anybody tell me why?
Probability of using those numbers.
One is probability, the processor, the way it is generating addresses, it is all 2 to the power I, and none of these numbers are 2 to the power I. So, it will never generate, that is one way. And if these are the addresses, none of the load instruction, all these addresses will be positive. Now, ideally when you verify the memory, you should have knew these constraints, you should not be trying to verify for everything and anything, but I am just simply saying when you put on the system, sure it opens some bugs, but it actually hides many more. Some of the bugs were previously not visible, it kind of makes those paths kind of easy to view, observable, but more often than not, it actually hides many scenarios, because although these primary input, it has all 0.5 probability and all that, very uniform, nice and fair story, but as it goes through the stages, the inputs and lines, everything imposes lot of constraint, and deeper this module in the design, what it comes to itself is kind of restricted. So, therefore, if you just do analysis and here and say, oh, it is vulnerable, but in real world that vulnerability or that power propagation, that information propagation could be suppressed. So, that is why it is an important kind of to look at that. So, there is a lot more details than that for obvious reason, but what I wanted to show you.
One question.
Yes, please.
So, what is those CR1, CR2 if you try to relate them with say AES?
So, one of them that is actually not correct, one of them you can think of SA.
So, one instruction for the entire SA.
But actually SA is also divided. I just wanted to say ECC also uses SA, then one more program also uses SA. So, whatever the subcomponents everybody uses, that is basically the thing.
So, this is publicly available also?
This is all it is like RISC-V, everything is publicly available for everybody. And you can
its implementation also available, very low.
All implementations are available for all RISC-V, instruction set extension, anybody did any analysis, anybody identified any problems, everything is publicly available. So, now as expected when we run on the AES, so there are two kind of variation of cryptographic extension that is available in the public. One is its name is crypto, another's name is X crypto. So, we looked at two modules in them, one is AES mix, you asked me what are those CR1, CR2, it is AES mix and it is a AES sub, right. So, it is really the mixing functionality and subtract functionality, and as you can see the expected power and the observed power is exactly matches. So, you can exactly figure out what is going on by doing simply the power analysis. And many of these implementation did not use many of the mitigation technique, they being open source and the first time, eventually they will do. When you run, you will probably not observe such a beautiful scenario, but once you kind of, so same thing for SHA.
Hello, I have one question.
Yes, please.
So, this instructions may not be real 32-bit instructions kind of thing, input data particularly.
Yes.
It may not be 2, 3, maybe more number of data may be needed. So, you require separate different kind of interface for this kind of instructions maybe some ROCC extension kind of thing.
You are talking about this instruction set extension, right?
Yeah, particularly CR1, CRN.
So
maybe not small instruction, maybe bigger instructions.
Right. So, these are already defined, this could be modified, I do not think it is a gold standard, but exactly the way add, subtract, multiply, the instruction set for RISC-V has been defined. Can we change it? Sure, we can propose if there is a reason, but these are also defined. So, by looking at all the functions of all the cryptographic and what are the common few instruction or 5-10 instruction, they define those code.
No, but for decoding and sending data for that.
Oh, that has been incorporated in the decoder of RISC-V.
Yeah.
So, it is not the original RISC-V. The RISC-V that support cryptographic instruction set extension, the X crypto and the crypto one, they have that additional logic that will distinguish these instructions.
Okay, so this
So
is
basically,
we cannot say it is a instruction set extension from RISC, but it is actually separate cryptographic processor having a different set of.
RISC-V has at least 2 if not 3 instruction set manual, one for original one which does not have any of those, another for the people who are interested in operating system kernel level programming, that is a privileged one. Unlike most processor where everything in the same manual, they have 3 different manual, and the third one will have just the cryptographic extension. Right. So, for AES also it is completely full recovery of data. For SHA also same 2 modules crypto and X crypto, SHA 256 and SHA 512, it is the full recovery. Now, we also wanted to look at that if we kind of use different type of mitigation like the operation blinding or some affine masking and all that stuff, if you want to do that, So then what happens to the thing? So this affine one seems to be kind of passing, that means the attack is not successful, but the blinding, we saw that blinding story earlier, the blinding actually fails the leak down test, that means we will be able to figure out the values or whatever, or key whatever we are trying to figure out.
What is this p value and CPA and DPA, what is that?
So this is this one is
Differential.
differential power analysis, this one is correlation power analysis, thank you, correlation power, and the p value is the p value obtained, and I am guessing when it says fail it's below the p value of what is assumed to be statistical probability, below which you know that.
So here affine masking means you marks those instruction and check, or what is that?
I need to double check, but this is the mitigation of masking, and
This is your work, right, or your
this
group
is
work?
our work, yes, yes. Affine masking is, I think this affine masking actually this solution exists, we just applied that on the instructions.
The TVL is exactly the same that you do TVL for AES, or
So there is a little bit of difference, and some of those differences are basically one is test generation, of course, then victim identification, then boundary, and fourth is doing on the unit level and then on the system level. So there are just few those minor differences, otherwise it is TVLA. So this is basically a logical point, and we can take a break, or I do not know, 15-20 minutes, half an hour, I am not sure. How many of you have energy to continue, or you want to take a break and come?
take a short break, 15 minutes.
Okay, sounds good.